So without further ado, Idan, the stage is yours.
Thanks, Nati, and hello, everyone. First of all, thanks for the TLV Deep Learning Bootcamp for hosting this event. This is the second time they host our competitions launch event, and we're very happy about this cooperation and hope we can keep on cooperating on future competitions. I will speak for the next, in the next hour, me, Neta, and Shai, we're going to speak about the competition. I'm going to speak with about 10 minutes about this general brief overview of the competition. And then I'm going to let Neta and Shai explain the dataset and the baseline model in a more detailed aspect of all of the information that is relevant to the competition. So just some quick background. MAFAT Challenge is a series of data science competitions that are fully open to the general public, hosted by the Israeli DDR&D and organized by Webiks. We had some previous competitions in the past. In 2018, we had a fine-grained classification of objects in aerial imagery in 2018. We had in 2020 the radar challenge, when we asked competitors to distinguish between humans and animals in radar tracks. And last year we finished the Wi-Fi challenge competition, where we asked competitors to determine whether a room has a human presence in it using Wi-Fi RSSI signals. And in this competition, we asked competitors to detect objects of certain classes from diversified satellite images. And really the emphasis is on the diversity of the dataset. The dataset contains 10,000 satellite images of 17 different areas of interest across the Middle East. Each image has the metadata of the resolution that the image was taken in, the sun elevation, the azimuth, and the sun azimuth. And this is the main object classes that are available in the annotated dataset. We have vehicles, small vehicle, medium vehicle, and large vehicle, double trailer trucks, and buses, small and large airplanes, and small, medium, and large vessels, heavy equipment vehicles, containers, and pylons. And you can see some examples from the actual data set, some vehicles, the container, the pylon, for example, and some aircraft, some marine vessels, small, medium, and large. And so we talked about the diversity in the data set, and this is what makes this task very difficult. And the first aspect of diversity is the resolution. You can see here the two examples, but the best images of the resolution are about from 40 centimeters to pixel to about 1.3 meter per pixel. So again, the diversity that you can see you can see the exact object, but in a completely different pixel area or a different visual representation because of the different resolution. Some of the objects are completely different by their sizes. Some of the object classes sizes are about hundreds of meters, like the boat on the left, and some of them just a few meters long, like the tiny cars on the right. So again, huge diversity. And another important aspect is that we have some object classes that are visually similar, but can only be distinguished by their context. For example, on the left, you can see these white rectangles that we know they are buses because of the context of the roads and all of the areas that they are placed in. And on the right, we can understand that the same white rectangle is a container because we can see it in the context of a port. But just by looking on the exact details of the actual object, it's hard to determine whether to which object class this object is part of, and this is another important aspect. There is varying object density within the images. Some of them are highly dense urban areas, or some of them are desert-like sparse areas with almost no objects in the image. And I think this is the most important aspect, the angle that the image was taken in. On the left, you can see a very vertical point of view, and on the right, a very oblique point of view, and the visual representation of the object is completely different And again, this is the same airplane's parking lot, but the actual object representation is completely different. And the last aspect that makes this difficult is that the objects are annotated as oriented bounding boxes, as you can see on the left. And it's unlike the common annotation of horizontal bounding box as you see on the right. And of course, this is done to better detect objects in arbitrary orientations, but this method may not be compatible out of the box with most current object detection models. So this is another aspect that might be challenging for the competitors in this competition. The overall timeline is going to start today with the meetup. Then we're going to have about 3 months of the public stage. On April 20, we're going to start the private stage for 1 week, and then the competition end will be on April 27. And then we will evaluate all of the submission and announce the winners. Total prize pool is $45,000, and top place get $20,000. As you can see, the distribution of the other 4 places and the distribution of the prizes. All of the information I just gave you, if you want to go through it again, and if you want all of the information about the competition, you can find on the competition platform hosted on Codalab. You have the link in the YouTube channel description. You can just look on Google, write MAFAT challenge, and again, you will get this for the same place. And just access Codalab and look for this competition. I will give you, for another 2 or 3 minutes, some explanation about what you can find in the platform. So you have the general timeline on the upper part of the website. Then you have 5 tabs. The first one is Learn the Details, where you can find most of the relevant information. You have the overview with practically what I just told you about why this is a difficult task, and some more information about model drift that Nadav is going to speak more about later in this meetup, the phases of the competition, and the code submission format. And then you have the updates tab, when we're going to keep you posted with all of the relevant information. At the moment, there's not a lot to know, just for the meetup that we are all experiencing right now, but we're going to post here a lot of more relevant information. And then you have the dataset tab, that here you can get all of the information regarding the data, the diversity of the imagery explanations, the actual dataset structure, the file description, and some information about the additional data about unlabeled training images that we also supply the competitors with in this competition. And the main data annotation guidelines, the annotation format, and the explanation for each object class. What is the main guidelines for annotating this object class, and some real life examples from the dataset that you can understand better the characteristics of each object class. The prediction and evaluation section, you can get explanation about the predictions and the evaluation metrics. Terms and conditions is all of the competition rules. I really suggest that you go through all of them and understand what we expect from you as the general guidelines to compete in this competition. Frequently asked questions. We gathered all of the relevant questions that we believe that will interest you and you probably would want to ask us, and provided an answer. I think there's like an answer for 80% of the questions within this page. But again, you can feel free to just click on the forums and post a question if you don't find your answer here. In the resources tab, we got some resources that will be interesting for you to go through when you start dealing with this data set. And the timeline, you get all of the important dates and all of the important deadlines. I will speak about the deadlines later, but all of the important deadlines that are part of the competition. If you want to compete in a team, then go to the Teams tab and get all of the instructions to how to create a team with your teammates, and how to you need to fill out a form, give us some information about the team, and then we're going to send you back the confirmation. If you want to compete as a team, this is the place you need to read and understand how to do it. In the phases tab, there's general information about the timeline of the competition. The participate tab, you can only enter here once you register for the competition. You need to have a CodaLab user and just to log in, and then you will be able to enter this tab. Here you got a link to the full data set, to the additional data unlabeled training images, the EDA notebook, and the baseline model notebook. The result is probably the most interesting part of the competition. It's the leaderboard. At the moment, you can see only one submission, which is our baseline model, and this is the score of our baseline model. And in the forums, you can, as I said earlier, you can post some questions or whatever you want to get from us, from the organizers, and we will try to answer as fast as possible. And there are two important posts that you need to know. One of them is Python packages, where you have information about all of the packages that are already installed in the submission Docker environment. You can see all of the list of all of the packages that are installed and their versions. And also there's an external data declaration for one. When you will read the rules, you will understand that if you want to use external data, like datasets or pre-trained models, you need to declare it in the forum. You have to do it until 30 days before the end of the competition, and this is the way, the place in the competition that you will need to declare it. That's it. So this is like the main brief overview of the CodaLab of the competition, and now I will let Neta explain more about the dataset. I forgot to say that earlier, the part of our hour, we're going to keep about 15 or 20 minutes for a question and answer. So you can post questions in the YouTube chat window, and we will try to answer some of the questions later. Thanks.
Okay. Hi everyone. Now we will present you our unique data. On the competition website, the training data is already available. You can download it from here. The training data set includes 1,400 grayscale frames and their label and the metadata files. There is also a download link for additional data unlabeled training images and metadata. You can use that data to leverage unsupervised or semi-supervised algorithms, as well as supervised object detection method. You can use this data as long as the frames are not manually annotated. Okay, and now I would like to show you the EDA. The main goal of the EDA is to learn about training data distribution, and it also provides you a soft landing and a quick start. The link is here. Okay. In the beginning, you can see the metadata field. Now, all the frames and all the objects from all the classes are automatically annotated, except for one category, a small vehicle. Small vehicle is a tiny object with high frequency, and therefore some of the frames without small vehicle labeling. The field in the left column here in the metadata, hermetic small vehicle, is a Boolean variable that indicates if all the small vehicles in specific frame was labeled or not labeled. Okay, here you can see the classes and the total number for each class. Then you can see a lot of statistics and analysis about the frames, the metadata fields, the AOI, and all the classes. And I would like to take a minute to present you. Okay, this heat map. Okay, this heat map it shows the distribution of resolution in each class. The brighter the color, the more objects are at specific resolution. For example, in the double trailer type, you can see that more than 50% of the double trailers are in resolution between 0.5 to 0.6 meter. Okay. And now I would like to show you some samples that emphasize some guidelines annotations. How about that? Okay, in this first example, you can see that the bounding box rotated and the bounding box located as tight as possible to the object. Okay. Okay. There you can see there are pylons here. So now the shadow of the pylon is included in the bounding box, and only the pylons are tagged along with the shadow. Okay, here you can see that the vertices of some of the bounding box are outside of the frame boundaries. Therefore, you should be expected to encounter some negative values pixels. Okay, in this frame, there aren't any annotation. So keep in mind that some of the frames are empty from objects. And this is the last example. Okay, here you can see there are many cars, but the class small vehicle wasn't annotated here. And accordingly, the field hermetic small vehicle in the metadata file, as I mentioned, is set to false. And that's it. Next, Shai will present you the baseline model. Good luck, everyone.
Hello, everyone. I'm going now to present our baseline model. You can find the baseline Jupyter Notebook under the Participate tab. Just click on the baseline model and you will be redirected to our Colab notebook. So this is our notebook. We'll just go over the main parts of it. Of course, later you can edit it, do whatever you want, but it's a good starting point for everyone to process the data and build a basic model and create a submission in the correct format. Okay, so first of all, downloading the data. For this demonstration, we created a mini data set. It contains just a few images out of the full data set. If you want to use this notebook as it is, you can change this field from a mini data set to full data set. So we just press on the cells, it downloads the data. Next, we are preparing the data for training. From our experiments, we found that small objects in the images are very hard to detect. Even with the models with the state-of-the-art models we used and tried. So we created a splitting script that allows for splitting the images to smaller frames of 640 pixels by 640 pixels. We recommend you do this or something similar to that. Of course, you can pull any other augmentations that you find useful. The scripts are all available here. I'll just go over the configuration data of this script, just so it will be clear what we have done here. So this is the configuration file for the splitting script. You need to state which folder has the images, which has the annotation data, the size of the splits you want, and the gaps between the splits. You can see here that we took sizes of 640 pixels and gaps of 320. That means there's a 50% overlap between the images. So we created a lot more data from a very small set of images in the mini dataset. The full dataset has a lot more, so you might want to do different kind of gaps or however you see fit. Okay, so once you split data into smaller frames, we added a really basic splitting mechanism to divide the data set into train and validation sets. So just run these cells and you'll have two folders with the data. You can see here the train data and the validation data here on the left. Okay, next is just training the model. Here we are using models from the MMRotate GitHub repository from OpenMMLab. This is a very good starting point for everyone who is not familiar with rotated object detection and satellite imagery. There's a lot of explanations in this repository about conventions in rotating bounding boxes. Also, they have a fairly large model zoo that you can try. Our example uses the the Reddit model, which is currently the state of the art on the DOTA dataset, which is also a fairly common dataset in this field. Is somewhat similar to ours, but not exactly the same. So we recommend you start with this repository. Okay, so once you install the packages, and you can follow along the installation process we did here, you download the pre-trained models that were trained on the DOTA dataset, define the classes, and then next you define the custom datasets for this competition. We follow the guidelines that the MMRotate repository stated. And we had to edit the functions to allow you to process the images of our dataset. They differ a little bit from the DOTA dataset. So just pay attention. We use TIFF images, so this was changed. And next, we also changed the processing pipeline of the image. The DOTA dataset images are RGB images, and our 8-bit images. Our images are 16-bit grayscale images. So a bit of changes were made here. Of course, you can change it to however you see fit. That's that. Okay, the next part is the training config. Here we made some adaptations to our own data sets. We changed the normalization values of the images that enters the network. It's very different from common normalization values because the images in our data set are 16-bit images. You might want to edit those if you see that, if you find different ways and methods to configure those, but these are the mean and standard deviation values that we found. Also, you can define different heads, depends on the model. Just when you use, if you try to use a different model than what we used, you'll have to edit a few more values here. So pay attention to what needs to be edited. Okay. Next part is the actual training. We're not going to run a training right now. I'll just go over a bit of the outputs that the training outputs. On each iteration of the training process, you can see the time until it finishes, and some data about the loss function and how it progresses. And once everything is done, you can you can deploy your model. In this example, we only did 4 epochs on the mini data set just to show how it works. It will probably won't output good results. The real training we have done before with the full data set and with the same model in this notebook, you already saw the results it got. Okay, so now let's move on to how you deploy the model. So first of all, you run this cell, which defines the model.py file. I'll open it on the side, so it will be a bit more comfortable to see. Okay, this Python file has a few mandatory functions and classes that it must contain. First of all, it must be named model.py, since our code searches for a file with this name. Second part that is very important is that you keep the class name model. Don't change this because we're expecting that also. Next, you must define the following 3 functions: a init function, a load function, and predict function. In the init function, you just init everything that you see fit, whatever you need for your model, classes, and any other variables that you might need to use. The only mandatory part here is this variable, the make initial pass over dataset. This is a Boolean variable. I'll talk about what it does in a few minutes. The second function that you must implement is the load function. You have to keep this signature with the dir path. You don't need to put everything here. This is for our own code to set the dir where the model is expected to be found. And here you load the model, set it to eval or whatever you need to do. Finally, the predict function. This function gets an image and the metadata that fits the image. It gets the image as a NumPy array and the metadata as a dictionary. In our example, you can see that we are using a sophisticated way to get to infer on a large image. The images that we will input to your model will be of size 1,280 pixels over 1,280 pixels. And you saw that our model was trained on 640 by 640 images. So this function, which is part of the rotate package, allows you to infer on smaller images. It just takes patches and infer, and at the end of the sub patches, it concatenate all the outputs that the model predicted. Okay, so these are the 3 functions that you must create. Next, if you set this variable, the make initial pass over dataset, to true, you are allowing your model to calibrate itself for the test data. What does that mean? You'll get one pass over the data to collect statistics, to figure things out, whatever you think that could help your model fit the test data better than as it was before. What do you mean by that? If you set it to true, you'll need to define 2 more functions. The first function is the collect statistics iter. It gets the same arguments as the predict function. And what it does, it allows you process the image and the metadata, one image and one metadata at a time. And you can collect all the information you gather into the variables you defined before. For this example, we defined another function called mean and STD that gets the image and collects the mean and STD values for this image, and it collects all the data from all the images and finally sets it to something. After you finish collecting the statistics, the next function that will be called is the update model function. In this example, we take the standard deviation and the mean values we found in the previous step and set the normalization process that we do during the inference with these values. Okay, so once you have all these and your model is ready, you need to package everything into a submission. So what this submission includes? It includes the model.py file. It includes a metadata file, which this cell will create. You don't need to change, you don't need to change anything in this cell. Just run it and the file will be created. The next part, there are two options for a submission. The first option is if the total size of your files is under 300 megabytes, you just need to zip them all up together and you can submit them through the website, through the Codalab website. So you need your model.py, in our case, you need a config Reddit file, which sets the configuration. You need a model weights and you need a metadata. You zip them all up and you can submit this file. In the case that your submission files are over 300 megabytes, but under 1 gigabyte, which is the maximum size of submission that we allow in this competition, you can submit the model via URL. What does that mean? You'll have to upload your model, your weights. It could be even the entire files, but we recommend it will be just the weights into Google Drive or any other URL that can be downloaded. It just needs to be a zip file that we download. And you set the URL path in this cell and run it. It will create a file called model URL.txt. And when you submit it, you'll submit the model file, in our case, the config, and the model URL.txt and the metadata. Our code will read the model URL and download your model. So for example, I'll show you how to get the link for the URL that we've put here. In this example, I'll use the Google Drive links. So I uploaded before a zip file with the weights that I wanted. I right click on it, press share. I make sure that here it's set to anyone with a link. Copy the link. Place it in this cell and run it. Now we have a file with the downloadable link. Finally, once you're all done, you'll have a submission zip file. Here we have two submission zip files, one a regular one and one with the URL. You can go to the Codalab competition website. Under the participate tab, you'll have the submit/view results. Here you can see the submissions we've done before with our baseline model. The baseline models are already available for download and you can download and submit them right away. They are under participate, dataset, and provided scripts. You can find them here. One example is the regular submission, and the other one is it's the same model but with the URL. So you could, if the explanation wasn't clear, you're welcome to look at the files and see for yourself. Okay, so finally the results. We have submitted the baseline models. We got a score of mean average precision of 33.8. And if you want to look at your results per class. You press on the view scoring output log. It will download a text file with the scoring log outputs. So here we can see our mean average precision and the score for each class. Okay, the scores goes from 0 to 100. So we can see that our model is not doing very well on small vehicles and got a pretty good score on large vessels. I hope this would help you get a good start on the competition, and we will now take some questions.
Okay, great. So thank you, Shai and Neta and Idan. So as far as questions are concerned, we have Mitchell. Okay, great. So we have Mitchell asking about the license of the data and labels, or which kind of license does the data have? Idan?
Yeah, I will take that question. You can see in the competition rules that this is stated that you cannot use the data set without not for non-commercial, commercial, or educational reasons, without getting the permission, written permission of the Israeli, the MAFAT team. So at the moment, it is not for non-commercial, commercial, or educational use. And you can ask for a special permission, and they might approve it, but at the moment it is not open for general use.
Okay, great. So the next question would be, how far into the competition can someone join the competition, and what is the last date for formulating a team?
Yeah, so I will take this one as well. You can enter the competition a day before the public test, the public phase ends on April 20th. So you have lots of time, and we do know from previous competition that some of the top places get to the competition in the last 2 or 3 weeks. So even if you see this recorded video on a later stage in the competition, don't be afraid, and we encourage you to join the competition. You still have a good chance and getting to the top places. The other question was about when you can merge a team and things. So it's a week before the end of the public phase. It's April 13th. You can see all of the information in the Codalab, the timeline tab. You have all of these important dates.
Awesome. Next question would be, where do we find the resources that both Neta and Shai presented? So Leah asked it and already found it, but I think it would be good to disclose for the rest to save them the search.
I'll take this one. All the data and the notebooks we presented are available in under the Participate tab in the Codalab website.
Awesome. So just upon registering and joining the competition, you are exposed to it, right?
Yes.
Great. So next question would be about using the test data in real life. So I guess I can take this one. It depends on whether or not you are the one that defining your test data. If you define your own test data, so probably you can use it later for like ongoing learning or something like that. And if the test data is not something you use, let's suppose it belongs to a client or something that is not disclosed at all. So obviously you cannot use it, or maybe even don't know what it is going to look like. And I think this is one of the nice things about this competition. So we are having a 2-stage competition in which not only we need to do good for data that we are exposed through the initial stage, but other can fit or make adjustments for things that change during the competition. And feel free, Idan and Shai, Neta, to correct me if I got something wrong.
Yeah, sounds good to me. Shai, you want to add something?
Yeah. Well, you got it right.
Thanks.
Exactly.
Awesome. So another question is about the limitation on runtime of the model on your end, probably for the testing.
Yeah, I'll take this one.
Go ahead.
The models are ran on a common commercial machine. So as long as you're under 2 seconds predicting per image, you should be good. The total amount of time that is allowed to make a prediction in the public phase is limited to 620 seconds, which if you divide it by the number of images, and we also added additional time, but if you divide it by the number of images, it's about 2 seconds per image. So as long as you can predict the entire data set and do your statistics calculations under 620 seconds, you should be fine.
I think it would be good idea to state what kind of hardware are we running on, so that things could be tested.
Yeah, it's stated on the website.
Awesome, great. So next question would be about the EDA. I guess we answered that already before. And is there an obligation to calibrate on the test set? So I assume there's no obligation to do it, but probably you're likely to want to do it to be competitive. Next would be, what are the satellites, which types and brands of satellites? Idan, would you like to take this one?
Yeah, I'll take this one. We cannot get into details on this one, unfortunately. But I'm sure all of you can just go down the data set and get some better information about these images and the general characteristics, but we cannot go specific about the satellites.
Awesome. So next question would be about the accuracy level of different categories. Is there is it going to be a simple mean, or do we have a weighting, different weighting per each class, per size of classes? Go ahead.
Yeah, I'll take this one. We use the mean average precision. That means all the classes have the same weight, and they are all equal.
And yet, if I get it correctly, so if we have less samples of some classes, then those classes would be of higher significance, right?
Yes. However, we try to make the data set as balanced.
Yeah. Awesome. Great. So I think we got it about the questions. So if there aren't any additional ones, we would transfer the mic to Nadav Barak from Deepchecks, who will guide us through drift detection and how is it, how does it affect, and how does it relate to the competition data? So Nadav, the stage is yours.
Thank you. One second, I will share my screen. Do you see it okay? Yes. Idan, is my screen okay?
Yeah, we see your screen perfectly. You can go ahead.
Perfect. So, hi everyone. My name is Nadav Barak, and today we'll be discussing drift detection in structured and unstructured data. Similar to the presentation before me, you can write question in the chat on the YouTube channel, and I'll try to get to answer as many of them as I can by the end of the lecture. So let's get started. So a little bit about me. I've been in research for about 5 years, first in academia and currently as a machine learning researcher at Deepchecks. Deepchecks was founded 3 years ago and mainly deals with testing and monitoring machine learning pipelines. We have an extensive open source offering, which I will demonstrate a small portion of it at this talk, which you can later utilize in the MAFAT challenge. Okay, so what are we going to talk about today? We are going to start with a high-level overview of why testing in general and what should we test. Then we'll do a drill down into drift. What is it? Why is it important? We'll continue with a live code demonstration of drift detection in structured data, where we will go over the main concept of drift and the statistical methods to detect it. Then we will apply the methods we learned in structured data for the domain of unstructured data. And we will finish off with techniques for drift mitigation. So let's get started. Okay, so why testing? What can go wrong? As you may know, there are many things that can go wrong when using machine learning pipelines. Experienced people in the crowd must have encountered some of the bullets listed here, if not most of them. Pitfalls can be found at the data collection phase, at the feature engineering, or in the model training and evaluation. It is important to test them in different steps of your pipeline when setting it up, and to monitor them over time for models in productions. In this talk, we will focus on the data distribution and especially drift, which is especially prominent in the MAFAT challenge dataset. So what is drift? Drift is a situation where the data, the label, or the relationship between the data and the label changes over time. It can be categorized into two broad categories. We have the data drift, in which the data itself changes over time, the distribution of it. And we have concept drift, where the data distribution does not change over time, but rather the relationship between the data and the label. I will simplify with an example. Let's imagine we are a company that buys and sells houses, and we have a model that gets a house detail, such as house type, the size of the house, etc., and predicts its market cost. Classic regression problem that I'm sure many of you have encountered before. Example for a data drift would be that over time, the percentage of small size apartment increases, meaning if in the training dataset, 20% of our houses were small apartments, then maybe now, as time goes on, we have 60% of our dataset containing small apartments, and let's say less private houses or big apartments. This is an example for data drift. For concept drift, let's imagine that the data distribution remained exactly the same, but rather, for some unknown reason, penthouse apartments became a more luxury product, which more people desire. For this case, an average penthouse apartment, which in our training set may have been at an average cost of $1 million, now is its market price is around $5 million. The data remain the same apartment that used to cost $1 million now costs $5 million. Okay, so we have covered what is drift. The obvious follow-up question is, Why do we care? Why is drift important? There are many reasons, but in my opinion, 2 reasons stands out. The first one is expectability. A key requirement of company stakeholders before deploying a model in production is trust. You need to be able to guarantee the model approximate behavior across different metrics and different data segments. You want to make sure that your model isn't performing especially bad at a specific segment which is important for your company stakeholders, and you want to be able to guarantee how it will behave in the real world scenario. And the second reason is, of course, performance. Drifted production data commonly mean deterioration in performance. If we would go back to the scenario demonstrated in the previous slide, let's say that indeed we had a data drift on small apartments, which now become much more prominent. Let's imagine that our original model trained on the training set had mediocre performance on small apartments. Maybe then, in comparison to the other data segments available, we said, oh, that scenario is not too bad because our model did a great job on all the other data segments. But now, when the small apartments ratio in the data increased from 20% to 60%, that is now a much bigger problem. For the case of concept drift, it is much more straightforward. Let's imagine that our model was trained on a training set where an average penthouse apartment was worth roughly $1 million. If our model is amazing, it will predict an average price of $1 million for a penthouse apartment. But if now the same apartment now is worth $5 million in the current market, this means our model is way off its true label. Okay, so we have established the drift is important. The next step that we would like to do, given that information, is detect it. We want to know if the scenario we are going to apply our model into has drift, or has drift been inserted slowly into the environment in which our model operates. For that, I will go into a notebook I have pre-prepared in which I will demonstrate several methods and techniques to detect such drift. So let's see if it works. Hoping that you still see my notebook just fine. If not, someone write something. Okay. So for this example, we're going to use one of sklearn datasets, the diabetes dataset. I will increase the font a little bit. Basically, in this dataset, we have information about patients, and the target variable is the average blood sugar of that patient during one periodic year. So, as we can see, we have several parameters, age, X, BMI, etc. The first thing we are going to do is insert a simplest possible drift. We are going to insert univariate drift into the age variable. How are we going to do it specifically? We're going to take the entire data set and split it into a train and test data set in such a manner that the trained data set will contain a larger portion of young people, and the test data set will contain a larger portion of elderly people. After we have created this synthetic split, which is, of course, drifted, I would like to demonstrate to you that everything I've talked about in the previous slides actually hold some water. So I'm gonna take my training data set. I'm gonna split it into a training and a validation set. And I'm gonna train a simple regression model based on the training portion of my data. Then I'm gonna test this simple model I've trained on both my validation or holdout set, which has the same distribution as my trained data set, and on my test data set, which is, as I mentioned before, drifted. It has a different data distribution. As we can see here, the model performs much better on the validation set. The validation set, which has a similar distribution to the trained data set, rather than on the test set. Meaning for this specific use case that the model was trained to be better on a younger personnel, since they are the majority on the training set, and it performs worse on elderly people. Okay, so let's get back to our original goal here. We have inserted univariate drift. Now let's try to detect it. The main second, I have a problem with the battery here. Sorry about that. So we are going to try to detect this univariate drift I've inserted. We're going to do it with the help of Deepchecks statistical test. Specifically, we are going to use Earth mover distance. So what is Earth mover distance? Let's go down to the figure below. So first, I'll explain what we are seeing in the figure. We have two cumulative distribution functions here. The blue one represents the trained distribution, and the green one represents the test distribution. What Earth mover's distance measures is, let's for a moment regard the trained distribution, the blue distribution, as a mountain, and similar for the green distribution. So we have two mountains, the blue mountain for the train and the green mountain for the test. What Earth mover distance roughly measures is how much earth or soil we have to move from the blue mountain and how far we have to move it in order to receive the green mountain. Here we can see that the distribution or mountains are quite different. There is a lot of earth to be moved, and therefore we get a high drift score. This is the analogy of what Earth mover distance actually calculates, which is the intersection of areas between those distribution functions. There are additional univariate statistical tests. Most common ones are a column of Smirnov and phi test for numerical features, and Kramer's V and PSI for categorical features. Again, those are tests to check for univariate drift. In a word about Kramer's V, here demonstrated on this sex feature, which has no apparent drift between the train and the set. Basically, it checks for the variation in quantity across all the different categories, the ratio of change for each category, then normalized by the size of the category and the number of total categories. Okay, so we have covered methods to detect simple types of drift, which are univariate drift on a single dimension. Now, let's move on for a more complicated example, specifically multivariate drift. First of all, we'll insert some multivariate drift, which is relatively explainable. What we are going to do in the following splits is we're gonna create a data split in which the train distribution will contain either elderly female or young males. And the test distribution will contain the exact opposite, meaning either elderly men's or young females. If we were to apply the same methods that I have demonstrated above, meaning methods to test for univariate drift on a single dimension, we can see here that no real drift is detected. That's because there is no substantial drift on a single dimension. If we take the age distribution between the train and the test, it's relatively similar, and same for the sex feature. The ratios between the train and the test are pretty much the same. So what can we do? there are two main approaches to handle multivariate drift. Let's start with the domain classifier, which is the more complicated approach, but in my experience works best. So domain classifier, hinted by his name, is at core a classifier. This classifier is trained to separate between trained samples and test samples. How does it do it? It takes the entire data set, trained samples and test sample, puts them together and label them accordingly. Label of 0 for samples that arrive from the train, label of 1 for samples that arrive from the test. Then we do the regular train test split. We train the domain classifier on a set of the data. Then we test it on another set of the data. The goal of the domain classifier is to separate the train and the test to distinguish which example came from where. If the train and the test are not drifted, meaning they came from the same distribution exactly, the domain classifier will have no ability to discriminate between them. The best it can do is do a coin flip and receive a really bad score. On the contrary, if the train and the test come from very different distribution, the domain classifier will have a very easy job. It will be able to separate and specifically say which example came from train and which example came from test. When we run our domain classifier on the train test split we have just done, we can see that it does a good job. One second, I'll increase the font size so you can see. It does a really good job. It has a really easy time separating between the train and the test. And furthermore, it also states that the age and the sex feature were the feature it used in order to do this separation between train and test. And specifically because it did such a good job, I imagine that it basically did the same synthetic separation that we did in our dataset. In real world cases, the separation is not that neat and clean, but still a domain classifier is a very powerful tool to indicate if you have multivariate drift and to spot you to the right direction on which features may cause this drift. I mentioned before that there are two methods, and I'm gonna discuss the more complicated methods. The simpler method is an extension of univariate methods, statistical test, to combine several features together. Most of those methods revolve around those features being of the same type. Specifically, most methods require all the features to be numerical. Some methods can handle both numerical and categorical drift, same as the domain classifier, even though from my personal experience, it is the more robust method. Okay, so we have covered on structured data methods to detect both univariate and multivariate drift. Now let's see how we can implement those methods in the unstructured domain. So I'll go back to the slide. Okay, so you can see the slide. Yes, okay. No, wait, that's my slides. Okay. Okay. So I think we're good. Drift in the unstructured data. So, one second. Unstructured in general include many data types within it. In this talk, I'm going to use examples from the world of computer vision and the world of NLP. What are the challenges when it comes to unstructured data? First of all, the main challenge is that values at a specific dimension, for example, pixel in an image, are not meaningful enough to explain drift. Even a combination of dimension, in most cases, will not represent the semantic essence of a drift. An example for such a semantic essence drift can be that you are in an object detection task, and the average size of the relevant object within an image changes. In some images, at the training dataset, it may be much bigger, and in the test dataset, the relevant object become much smaller. If you would monitor the change in a specific pixel or even a group of pixels, you would not be able to capture that specific drift. A secondary challenge is that usually the size of a single sample is just too large, which causes problems for statistical computations that stores the data in memory in order to do the drift calculation. So what can we do? How can we still apply the methods discussed in the structured domain in the unstructured domain? Here I'm going to present two approaches, one based on properties and the other one based on embeddings. So let's begin with properties. So what are properties? Properties are one-dimension values that are extracted from either the sample, the label, or the prediction. For example, in object detection, an image property can be brightness, and a label property can be average bounding box area. Quality properties should be explainable, domain relevant, and have the ability to explain different types of drift. In other words, for a property to catch drift, it must be correlated to the drift. For example, imagine you have a data set for animal classification. Your training data set had a big variety of different types of pictures of animals on a variety of backgrounds. But in the test data set, the percentage of nightlife animals increases. For this specific use case, if you would measure average brightness in an image, most likely you would detect drift as the test dataset contains much darker images taken in the nighttime. The problem in properties, as can be hinted from the example I've just said, is that it has a hard time capture drift on semantic dimension. In the example I mentioned, we had a strong correlation between the type of animals detected and the average brightness of an image. This is by far not the common use case. Yet, if you would have quality properties across a variety of areas, chances are, or there is a chance that one of those properties could capture a drift that takes place. In the graphs displayed here, you can see several examples of running the same univariate methods discussed for the structured data set on properties for visual data. Specifically, as mentioned above, properties are one-dimension values, meaning if you would take the average brightness of your entire dataset, you can treat it as it were a feature and run the same computation as we've seen before. Okay, so that's properties. We said the problem in properties is that they have a hard time capture drift on semantic dimension. Let's see how we can complete that puzzle with embeddings. So embedding. Embedding are a low-dimensional continuous vector representation of a sample, meaning a vector of numbers that represent each, in this case, image in the dataset. Quality embedding captures the essence of a sample such that semantically similar samples will have a similar embedding space. Now let's review the sample, the image on the bottom of the slide. In this image, each sample were a book, a full textual book. And these books were embedded using a neural network into a vector representation, which was still quite a large dimension. Then TSNE were applied to reduce the dimensionality of the embedding into 2 dimensions for visual purposes. As we can see here, if, for example, we will look at the science fiction subspace, we can see that 2 books that were both science fiction have embedding vectors which are much more closely related to one another, and also close on the 2-dimensional space. In comparison for, let's say, a science fiction book and let's say an historical novel, which are more far apart. So basically what we are observing here, that embeddings capture the semantic essence of the sample rather than, let's say, more flat properties of the sample, such as the language, tonation, word lengths, etc. So how can we use those vector representation to detect semantic drift between data sets? So in contrast to properties, the single dimension in an embedding space usually don't have any specific meaning. We said even the embedding space is a vector representation, but it can be quite a long vector. And each specific dimension in it doesn't have real meaning. Luckily, we have covered method to detect multivariate drift across different dimensions or features. Domain classifier to the rescue. In the example below, the purple points are examples that the domain classifier found to be more correlated to the training dataset, whereas the dark blue examples are examples that the domain classifier found to be more related to the test dataset. The main advantage of embedding over properties is that they capture complex semantic meaning. If we go back to the example of the previous slide, books of the same genre usually would be close together. So if, for example, in the training dataset, we had a lot more science fiction, and in the test dataset, we will get more history books, though this kind of method would catch it. The main disadvantage of this method is that in many cases, it will not be so explainable. The domain classifier will be able to highlight examples which are more native to the trained dataset or more native to the test dataset, but we will still have to give the added work of finding out what is the common ground of those examples, what is the root cause of the drift. Okay, so as of now, for the unstructured domain, we have covered 2 main approaches, properties and embeddings, which are basically tools to convert the problem from an unstructured sense into some form of a structured problem on which we can apply statistical tools and methods. How does it help you? Let's drill down specifically into the MAFAT challenge. In the MAFAT challenge, you will face a task of object detection under a drifted settings. You have 2 main alternatives for applying the drift method in object detection and tasks, specifically using the tools I've demonstrated in my notebook from Deepchecks. You can do the heavy lifting yourself, but get a lot more customizations by basically creating embedding or properties calculation function, running it across your entire train and test dataset, collect the relevant information for each dataset. In that point of time, you have 2, let's say, data frames containing the relevant properties and embeddings for the train and for the test. And then you can run the native Deepchecks drift detection checks. That's one alternative. The second one is to run directly the Deepchecks vision sub package. The main benefit of the second alternative over the first is that in addition to drift checks, you get for free the ability to run data integrity and model evaluation checks, as well as the ability to use the built-in properties. You don't have to come up and write everything from scratch yourself. The QR code will lead you to the landing page for the Deepchecks open source package. And also, if I've not mentioned it before, the notebook I've demonstrated before is also available on the description of the YouTube channel. Okay, so we get into the final section of this talk. Drift mitigation. We've discussed many methods how to detect drift and see if you are indeed in a drifted scenario. Now let's discuss how we can fix that. Given that I have discovered I am in a drifted scenario, what can I do about it to help my model from deteriorating? Okay, so there are two main approaches. The first approach is quite obvious. I have a drift, let's try and reduce this drift. For this also, there are two sub-options. If your train distribution does not agree with your test distribution, and obviously you cannot handle and modify your test distribution, then you should modify your train distribution. You can do it in one of two manners. One, you can remove stuff from your train distribution. You can remove either features or samples, and by doing so, you would make your train distribution look more similar to the test distribution. The problem in that, as I think many of you are now mumbling to yourself, is that we don't want to remove feature or samples from our trained dataset. Most likely the basic core of machine learning, even though it's getting questionable as we continue, is that the more data, the better the model. So in most scenarios, we would like to avoid it, but in some cases, removing problematic samples in order to make the train more similar to the test is a good idea. And the second method, which is more sophisticated, is adding synthetic example to the training set. And specifically, we want to add synthetic example in a manner that will make the train distribution more similar to the test distribution. Now, this has two main difficulties. The first one is that creating synthetic examples that are realistic is no easy task on its own. And more so for our purpose, we want to make synthetic example in order to make the train distribution more similar to the test, meaning that we will have to most likely create synthetic examples in regions which are less prominent in the training set. And this will be an even more difficult job, yet definitely feasible. The second approach to do drift mitigation is in fault modeling. We will not modify our training set at all, but rather we will select a model and a training procedure that takes into account the drift nature of the setting. One example on how to do that is to upweight train samples in regions that are more prominent in the test set. You have detected region in the train set that there is a lot of examples there for the test set, but you want your model to pay closer attention there. You can upweight them in such a manner that when your model is trained, it will be penalized more for making mistakes on those areas. The common thing for both of those methods is that it requires access to the different production data. which is luckily for you available for the MAFAT challenge. But also it requires finding the cause for the drift and the different train samples or regions to use for the mitigation process. This can be done by using all of the stuff I've mentioned in most of this lecture. Okay, so we have discussed why drift is important, how to find it in structured and specifically in unstructured data sets. We have discussed methods in how we can mitigate these drifts under several settings. And basically, this is the end of my presentation. I hope you found this talk informative. The presentation as well as the code presented are available online. For those of you who will use the Deepchecks package, I encourage you to give us feedback and suggestion on how to improve. Also, feel free to contact me if you have any questions. Thank you for listening and good luck in the challenge.
Great, thank you. Thank you, Nadav. And I don't see any questions in the chat, but I have few of my own. So first of all, would you consider cut and mix also to be a good way to mitigate the drift, like to scramble some of the existing images?
Yeah, that for sure can be a specific example of annotating, of getting synthetic examples. But the main goal function when you do that is to make sure you make the training set more similar, or at least to cover more of the domain compared to the test data set.
Great. So another question, probably less about the drift section, but more about the competition, is how are train and test separated? Or what kind of, I would extend that question to what kinds of drift should we expect? Is it going to be different angles, different stuff within the properties of the data, or as Nadav presented, would it be a concept drift? Shai, would you want to take that?
Yes, I'll take this one. First of all, in case they meant how's the train and test divided in the notebook, it's just a random split. So 2080 for train and validation. But if you talk about the real test data, the public test and the private test, we try to make them as similar as possible to the training data, but it's very difficult to do it under so many constraints. So there'll probably be a lot of drift in regards of the images, color variation, and probably also in the metadata.
Okay.
You are generous. I would have thought your answer would be, I'm not telling you, try to find out.
Yeah, that
have to calculate
that was my goal as well.
Online. As
Great.
you go.
So,
it's not that easy. So.
To be honest, I thought it would be varying in time of acquisition or things like that. That different times, different stuff. But honestly, I don't think I don't. To be honest, so I don't know anything about the data myself. So part of my questions are kind of audience questions. So thank you, Nadav, and thank you guys. I don't see any additional questions of the audience, and I wish good luck to all participants, and I invite all of you to join our future events. Hopefully they would be face-to-face events rather than online. I think that better collaboration and a good chance to meet with everyone in person is much greater experience, at least on my behalf. So thank you all. And good luck with the competition, and good luck for the participants. And see you all soon. Bye-bye.
For watching us.
Bye-bye.
Thanks. Bye-bye.